First of all, welcome you all to this live session one. My name is Akhilesh Goyal, and I am from IIT Bombay. I am a PMRF scholar, and from now onwards, I will be taking this live session throughout the course. And yeah, we are talking about the course ME120 Applied Thermodynamics. That is the advanced course after the basic thermodynamics. So in the first session, we will be solving questions related to the basic thermodynamics. We will be covering some of the concepts, and based on those concepts, we will be solving some of the questions. Okay, and you can ask questions. For asking questions, you have to type your question in the chat box. I will take those questions from the chat box. Okay. And here are 14 students, 14 or 12 students. uh, Others may join in between, so let us start the session. Yeah. So uh, so first of all, what is a system? So, and you have already listened about some two, three words, that is system, boundary, surroundings, and all those things. So, first of all, what is a system? So, system can be a quantity of matter or also can be a region in space. Okay, if it is a region in space, it is called as control volume. Okay, because we are considering a region or volume in a space, and if it is a quantity of matter, it is control mass. Okay, so so a quantity of matter, a mass, or some region in space upon which we are analyzing something, or we are under or the this part, that quantity of matter or region upon which attention is there, because we are solving some problem related to that matter or region is called as system, and everything else is called as surrounding, and the thin layer that separates this system and surrounding is called as boundary. Okay, and yeah, and how many types of systems are there? So there are three types of systems: open system, closed system, and isolated system. So these systems are classified according to mass and heat, how the mass and heat can interact with the system. Based on that, these three type of systems are classified. Okay, so the first system is open system. So you can see in the pictorial diagram as well. If in a system, mass as well as heat or energy can interact with the surroundings, then it is called as an open system. But if the interaction of energy is allowed but interaction of mass is not allowed, then it is called as a control, it is called as a closed system. And if the energy and mass both are not allowed to interact with the surroundings, then it is called as isolated system. Okay, so yeah, so open systems are also called as control volume. Closed systems are also called as control mass system. And what are the examples of these systems? So for open system, the example is air compressor, where a mass or air goes through the inlet, goes to the system, and a work is done on that air. That air is compressed because of the work is done there, and then air comes out in the high pressure. So mass interaction is there, mass is entering from one inlet and coming out from the outlet, and also work interaction or energy interaction is there, because the work is being transferred to the mass. Okay, so the mass transfer and energy transfer is there, so it is called as open system, and air compressor is the example of this system. Now the example of closed system is, so a cylinder bounded by a piston is example of closed system. So in a piston bounded cylinder, the mass is confined into that cylinder, mass cannot come out and the extra mass cannot go inside that cylinder, so mass interaction is not there, but the mass can expand or contract. In that way piston will go up or down, so in that way it can transfer the work transfer can happen there, the piston work. Also the walls may not be insulated, so heat transfer is also possible in that piston bounded cylinder. So this is an example of closed system. But in isolated system, as we know, the interaction of mass and interaction of heat both are not possible. So the example of this isolated system is hot coffee in a thermos. So when we put a hot coffee in a thermos, the coffee is confined into that thermos, so mass transfer is not possible there. But also that thermos is insulated from all around, so the heat transfer or energy transfer is also not there. So both are restricted in the isolated system. So hot coffee in a thermos is an example of an isolated system. Okay, so this is about all the three type of system. Next is the question. So, in what form can energy cross the boundaries of a closed system? Okay. So, in the previous slide, we saw that in a closed system, mass transfer is not possible, but energy transfer is possible, and energy can transfer uh, either in the form of work that we saw in the example of this uh, piston. Yeah, so we saw the example of piston bounded cylinder. So work is possible there because the piston work can be done there, as well as the walls are not insulated, so heat transfer is also possible there. So yeah, so here is what form can energy across the boundaries cross the boundaries of a closed system. So here is answer is heat and work. Heat is also possible and work is also possible. Yes, Mukesh Kumar, option B is right. Okay, so any doubt till here? Okay, so let's move to the next part. So
Hello,
next
sir.
is, yeah,
I have one doubt, sir.
yeah, ask.
In a closed system, जो in closed system valve is used or not?
Can you repeat please?
In a closed system example,
Yeah.
valve is used in a cylinder piston.
No. If valve is used, then mass can enter and exit from that cylinder. So that will be the case of an open system, not a closed system. Okay.
Okay, sir.
Yeah. So let's move to the next part. So yeah. So the next question is, on a hot summer day, a student turns his fan on when he leaves his room in the morning. When he returns in the evening, what will be the room's temperature? And assume all the doors and windows are kept closed. Okay, so let's assume there is a fan in the room. So orange box is in the room and this blue geometry you can see similar to the fan. So a fan is there in the room. Okay, and here it is given that all the doors and windows are kept closed. So it is a case of closed system because windows and doors are closed, so air cannot come inside and go out. So it is a closed system. Now consider this whole room as a system. Now we can see that there is no heat transfer, as there is assumption of doors and windows are kept closed, so mass transfer is not there and heat transfer is also not there. And then fan is running, so to run a fan we need to put some work inside that room, so in the form of electrical energy. So here we can see that if we consider the whole room as a system, it is a closed system where the work is being done on the system. So this work will convert into heat. So From the first law of thermodynamics, uh, we know dq is equal to du plus dw. So here no heat is being transferred, so dw is dq is 0. So 0 is equal to du plus dw, and the work is done on the system. So work is in the form of the this is the negative work. So the sign convention for work is, when the work is done on the system, it is a negative work, and if the work done by the system, it is a positive work. Okay, so it is a negative work, that is minus w. So here du is equal to w. So the internal energy of the inner environment or the system is increasing because the electric work is done to run the fan, and that work is inside that room. So the internal energy is increasing, and internal energy increasing means the temperature is also rising. Okay, so what are the options we have? So room will be cooler, no. Room will be warmer, yes, because the electrical work we are putting inside the room is being converted into internal energy of the room. That means the temperature is increasing, so room will be warmer. And there will be no chance this is wrong, and it cannot be said no it is also wrong, because we know room will be warmer. Okay, so guys, if you have any doubt you can ask here. Yes, Mukesh Kumar, option B is right. Okay, so any doubt you can ask, or we will move to the next question. Okay, so let's move to the next question. Yeah, so the next question is, yes, Moti Krishnan. So what Moti Krishnan asks, what if fan is switched off? So when the fan is switched off and your room is a closed system and no energy is being transferred, also no mass is being transferred, so it is an like an isolated system, so there will be no change in the room temperature. Okay, I hope I cleared your doubt. Okay, so what is the next question? Yeah, iced water is a pure substance. So first of all, we should know what is a pure substance. Okay, so pure substance means in a homogeneous chemical composition throughout the volume. Okay, so it doesn't matter what phase, solid, liquid or gas it is, but what matters for pure, for being pure substance is the chemical composition of that whole substance should be homogeneous throughout the whole this whole volume. Okay, so for iced water, it is a mixture of two phases, solid and liquid, but the chemical composition is constant throughout the system. So we can say iced water is a pure substance. So here the answer is true. Okay, so iced water is a pure substance, but what can be the other examples? Okay, so what if I mix oil and water? Will it be a pure substance? Or yeah, will it be a pure substance? So Rakesh say no, Moti Krishnan say no. Yeah, so yes, yeah. So yes, oil plus water is not a pure substance, because oil has a lower density compared to water. So once we mix the oil and water, oil will start separating from water and uh, collects at the top of water. So it is not an homogeneous mixture. So oil plus water solution cannot be called as pure substance. Okay, what if we mix what if we mix alcohol and water? Will it be pure substance? Some quick answers.
No, no, sir.
Mothi Krishnan say no. What about others?
No, sir.
No, sir. So the fact is, uh, alcohol plus water solution is a pure substance because alcohol and water mix properly and do not separate after putting them for some time. Okay, so alcohol plus water solution is an homogeneous mixture, chemically homogeneous mixture throughout the volume. Okay, so it is an pure substance. Okay, clear?
Yes, sir.
Yeah. Okay, so any doubt? No. So let's move to the next question. Yeah. So the next question is, yeah. So a person is cooking food for his family in a pan that is, the one condition is uncovered, the second condition is covered with a light lid, and the third condition is covered with a heavy lid. The question is, for which case will the cooking time will be shortest? Okay, so a person is cooking food and he has three options. He can put that pan uncovered, or he can put light lid, or he can put heavy lid. But which case will take shortest time? So for it, yeah. Uh, Soumyadeep mystery. Let's see. Let's discuss this question. Yeah. So this is the curve between pressure and temperature for water. Okay. So here you can see. So at this point, 101 kilopascal pressure and 100 degrees centigrade, we know that at atmospheric pressure, that is 101 kilopascal, water boils at 100 degrees centigrade. Okay, so this is the case when the pan is put uncovered. In that case, the atmospheric pressure is on the pan and the water starts boiling at 100 degrees centigrade. So in the pan, the temperature of steam or water vapors will be only 100 degrees centigrade. Okay, but if you put some more pressure, that how that is possible? If we cover that pan with a light lid, then this lid will put some pressure, because it will confine the water vapors and put some pressure on that vapor inside the pan. So let's assume it is somewhere here, because we are putting some pressure, say P1, that is a light pressure, and corresponding to that the water will boil at some temperature, let's assume 130 degrees centigrade. Okay, so the temperature of vapor in the pan will be at 130 degrees centigrade compared to 100 degrees centigrade. So the second case will take less time compared to the first case when uh, the pan is put uncovered. But what about the third option, when pan is covered with an heavy lid? So when the pan is covered with heavy lid, so for steam or vapor, it will take more pressure to lift that lid to escape. So this heavy lid exert more pressure onto the steam or vapor inside the pan. So corresponding to this higher pressure, the temperature of boiling will be higher, let's see 200 degrees centigrade. Okay, so in this case, in this second case, when the heavy lid is put on the pan, so higher pressure is there on the vapor. So the temperature, the vapor temperature inside the pan will be higher, let's say 200 degrees centigrade. So it will take lesser time compared to the second case. So we can say when more or more pressure is put, when the more or more pressure is there, the boiling pressure, boiling temperature of water is higher. So in cases A, B, and C, the most or the heaviest or most pressure is being put in the option C, or this uh, the case C, where the heavy lid is put on the pan. So it will put in the third case, vapor will have higher pressure, hence higher temperature, means less time for cooking. So the question is, for which case will be the cooking time be shortest? So it will be the case third, when the higher lid is put, higher heavy lid is put on the pan. Okay. So any doubt in here? Okay. So everyone answered option C. Yes. Answer. Option C is the correct answer. Okay. Yeah. So I hope all is clear till here. Yeah. Yeah. Someone asking?
I have a question.
Yeah.
Sir, what is light lead?
So lid is the cover you put on a
Yes,
pan. Okay,
yes,
so here light lid means compared to the third option, the weight of the lid is less.
yes, sir.
Okay, that means
Okay.
light lid here.
Yeah, okay, sir.
Yes, Nishant, ask.
No, sir. All clear.
You are not audible.
Sir, no doubt, sir.
No doubt. Okay, sure.
Okay.
Yeah, someone asked, due to altitude any change. So what happens at altitude? When we go up, the pressure decreases. Pressure decrease means, if we see here, if we go down from the atmospheric pressure, let's see, let's say we are going somewhere on some hill or some mountain where the pressure decreases to this value, let's see 80 kilopascal. On this pressure value, the uh, corresponding boiling point will also be lesser, say 70 degree centigrade. So from here you can clearly see it. When we go on altitudes, the pressure decreases. Pressure decrease means the boiling temperature is also decreasing, and that means it will take more time to cook the food at some altitude. Okay, so if you are cooking food in open pan, so it will take more time on mountains compared to fields. Okay, so Rakesh, I hope I answered your question. Yeah. So yeah, so let's move to the next part. So the next question is, a 600 megawatt steam power plant which is cooled by a nearby river has a thermal efficiency of 40%. Determine the rate of heat transfer to the river water. Okay. Yeah. So you can see, uh, so here in the question, the capacity of steam water plant is given, that is 600 megawatt. Okay, and it is cooled by a nearby river, and thermal efficiency is also given as 40%. and what is asked is heat transfer to the river water. Okay, so let's assume this steam power plant, see in this figure. So uh, let's assume this is a steam power plant, and this plant is this plant takes heat from hot source that is at temperature T1, and the amount of heat taken is Q1, and it converts a part of this heat Q1 into work W, and the remaining heat is transferred to the river water. Okay, that is Q2. So here the efficiency of this steam power plant neta is given as 40%. And what is the efficiency? Efficiency is the work produced W divided by the total heat
Heat
input
supplied.
Q1, right? So here the efficiency is given. Here efficiency is given as 40%, that means 0.4, and W, the work, the capacity of the steam power plant is also given, that is 600 megawatt, and the heat it takes from the hot source is Q1. So what will be the value of Q1 is 600 megawatt divided by 0.4. So that is 1500 megawatt. That is Q1. Okay. So this power plant, this steam power plant takes 1500 megawatt heat from the hot source T1, converts its 40%, that is 600 megawatt, into the work, and that remaining part is transferred to the river water. So what is the remaining part? So we have Q1.
900.
Yes. So we have Q1, that is heat taken from the hot source, that is 1500 megawatt. We have work that is converted, the part of this Q1 heat is converted into work, uh, that is 600 megawatt, and the amount of heat that is transferred to the river water Q2 is Q1 minus W, that is 1500 minus 600 megawatt. So Q2 heat rejected to the river water is 900 megawatt. Okay, so that is the answer. So yeah, Rakesh, Mukesh, your answer is correct. This is 900 megawatt of the energy of the heat is rejected to the river water, and 600 megawatt of the heat is converted into the water. Okay. So any doubt till here? Okay. So
No, sir.
if yeah. Okay. So let's move to the next part. So the next question is, does difference in enthalpy of saturated vapor and saturated liquid change with pressure? Okay. So what is the enthalpy of saturated vapor? That
Sir,
is
we can calculate.
no, no. Okay. So it varies with the temperature and pressure. So I am not asking about the values. So I'm telling this enthalpy of vapor is given as Hg, and the enthalpy of saturated liquid is given as Hf. So the difference of Hg and Hf, that is Hfg. So this HFG, difference between enthalpy of saturated vapor and saturated liquid, is also called as latent heat of vaporization. Okay. So the question here is, the difference of these two enthalpies, that means the latent heat of vaporization. So does this latent heat of vaporization change with pressure? Okay, so let's see how the this enthalpy changes with the pressure. So you can see in the figure, this is the diagram between pressure and enthalpy, and you can see the from the shape of this dome, when the pressure is increased, the difference, what is hg, what is hfg here, this width of the dome is hfg. Okay, because this side is vapor, so this line is for saturated vapor and this line is for saturated liquid. Okay, and and the difference between those lines, okay, so the width of this dome is hfg, that is latent heat of vaporization. So as we increase the pressure, you can see the width is also decreasing when we are going for high pressures, and this width is continuously decreasing till a point here. When we reach at this point, this latent heat of vaporization becomes zero, and this point is called as critical point. Okay, so at critical point, latent heat of vaporization is zero. At this point, if you still try to increase pressure, so at this point the liquid flashes instantly. It doesn't convert into two phase, it doesn't go into biphase phase. Okay, so from liquid it goes to vapor in flash. So that is a critical point. So here again, to reiterate it, when we increase the pressure, the latent heat of vaporization, or the difference between enthalpy of saturated vapor and saturated liquid, decreases, and at some point, that is the critical point, this difference becomes zero. Okay, so again, to read the question, does this difference change with pressure? Yes, it change with the pressure. As the pressure increases, this uh, difference between enthalpy of saturated vapor and saturated liquid decreases until a point, that is critical point. And at critical point, this difference becomes zero. Okay, so option 1 is correct. Yes, this latent heat of vaporization changes with the pressure. As we increase the pressure, this latent heat of vaporization decreases, and at point critical point, this becomes the value of this latent heat of vaporization becomes zero. Okay, so any doubt in this question? Okay, so so let's move to the next question. So yeah, so the next question is about exergy. So the question is, exergy is the blank space on the amount of work a
Sir,
device
sir.
can deliver without violating the laws of thermodynamics. Okay, so
Yes, ask Rakesh.
Sir, sir, variation with temperature, latent heat of vaporization, variation with temperature. Please show that also.
okay, Rakesh. So I have not included that chart in these slides. So maybe when we complete this session, I can show you that chart. and then you will understand that better. Okay, so let's keep this question for the last. Okay,
Okay,
I
sir.
will
Okay.
answer. Okay, till then we will cover the all other questions. Okay, fair, Rakesh? Yeah. So this next question is, the exergy is the lower, upper or minimum limit on the amount of work a device can deliver without violating the laws of thermodynamics. Okay, so what is the exergy? Yeah, so the definition of exergy is, the exergy is also called as available energy. So the exergy is the maximum work that can be obtained from a certain heat input in a cyclic engine in a specified environment. So you should focus on these highlighted words that are maximum work obtainable with a certain heat input in a cyclic engine in a specified environment. Okay, so when we talk about exergy, exergy also consider the environmental conditions. Okay, so in the second law we saw that how much work a engine can produce from a heat source, between heat source and sink, but actual engine works or runs between that heat source and environment. So here exergy take the consideration of environmental conditions. Okay, so here by the definition, exergy is the maximum work that can be obtained from a heat source or a particular heat input in a given specified environment condition. Okay, so if we have 100% of total energy, see here, if we have 100% of total energy, a part of this energy, the maximum part of this energy that can be converted into work is exergy, and the remaining part is unavailable energy. Okay, so the unavailable energy cannot be used, that cannot be converted into any work, but this exergy is the limit that can be used, that can be converted into the work. Okay, so here are some condition when we consider exergy. So in this condition, system starts from initial state and goes to the dead state. And what is dead state? Dead state is state of environment. Okay, so the environment condition is called as dead state, and to achieve that maximum work possible, you have to go from initial state to the dead state. And this exergy shows the upper limit of the work that can be delivered from a device. Okay, and also it is not the property of a system only, it is the property of system surrounding combination, because the exergy depends on environmental condition as well. If we vary the temperature of environment, the value of exergy will also change. So it is a property of system surrounding combination, not the property of a system, neither the property of the surrounding. It is the property of the system surrounding combination. Okay, so again go to the question. Here is exergy is the what, lower limit, upper limit, minimum, or what? So exergy is the upper limit on the amount of work a device can deliver without violating the laws of thermodynamics. Okay, so option B is the correct answer. This is not the lower limit, not the minimum limit, but it is the upper limit on the amount of work. Okay, so exergy is the maximum work obtainable from a heat input in the given environmental condition. As the environmental condition changes, the amount of exergy will also change. Okay, so yeah, any doubt in this question, in this concept, any doubt? Okay, Okay, so let's move to the next question or next concept. So what is the next concept? So yeah, so entropy principle. Okay, so from the Clausius inequality, I hope you guys watch the videos before this session. Those 2 3 videos given in the course. So if you watch those videos, you must know Clausius inequality. If you don't know, please go back and watch those videos. Those are more information full or like very good videos. You will get something from there. Okay. So for any infinitesimal process, the Clausius inequality tells the ds is greater or equal to dq by t. Okay, but for any isolated system, and in isolated system dq is 0. Okay, so for that isolated system, ds is greater or equal to dq by t, and here the q is 0 for isolated system, so ds isolated is greater or equal to 0. Okay, so this equation converts into this ds isolated greater or equal to 0 for isolated system. So again, if the process is reversible, this entropy change of isolated system is 0. That means entropy is constant for a reversible isolated system. Okay, but for an irreversible process, this inequality exists. So for an isolated irreversible process, entropy change will be greater than 0, and for reversible process this entropy change will be 0, means entropy will be constant. Okay, so here from these equations we can conclude that the entropy of an isolated system will never decrease, it will always increase, and it remains constant only for the reversible processes. Okay, so from starting from the Clausius inequality that tells ds is greater or equal to dq by t, for a reversible isolated system, this ds is equal to 0. That means entropy remains constant. But for irreversible isolated process or system, this ds will be greater than 0. That means the entropy of isolated system won't decrease, but it always increase. And for reversible process, it will be 0, or the entropy will remain constant. Okay, so this is the entropy principle, and to reiterate it, entropy of isolated system remains constant for reversible process and always increase for irreversible process. Okay, so based on this entropy principle we will see some questions. Okay, so yeah, so the next question is, based on the entropy principle, the entropy of universe always increase, always decrease, is 0, या फिर none of these options. So
Sir,
let's see.
always increases
Yeah. So let's
because
discuss. Yes, yes, please. Yeah.
universe is an example of isolated system.
Yes. So let's discuss this. So let's see, here is a system, and here is surrounding, and there is heat interaction between system and surrounding, that is q heat is being interacted between system and surrounding. Now we want to talk about universe. Okay, so if we consider this system and surrounding as a bigger system, okay, so this inner system, that green part, becomes a subsystem of this bigger system. So in that case, this the bigger system which contains this small system and surrounding is also a system, but it doesn't interact with the outside, because the universe, if we consider it as an universe, so universe doesn't interact with outside. So this universe, in this universe, no heat is being transferred, no work is being transferred between this system that is that is universe and outside of it. Okay, so considering this as a bigger system that is universe and that doesn't interact with outside, that means this is an isolated system where no mass transfer is there, no heat is transferred, and no work is transferred. So it is a case of isolated system, and whatever happens in this system is a spontaneous process. If we consider it, if we consider that no external factor is applied into this universe, then whatever happens inside this universe are a spontaneous process, and and those processes are full of irreversibility. Okay, so we can say that universe, if we consider the whole universe goes through spontaneous processes, those are irreversible processes. And for irreversible process, this delta S is greater than 0, that we saw in the last slide where we talked about entropy principle. Okay, so based on the entropy principle, the entropy of universe will always increase. Yes, the entropy of universe will always increase because it goes through the spontaneous processes or irreversible processes. That means the entropy of that universe will always increase. Okay, so option 1 is correct. Always decrease, it is wrong. Is always 0? No, because universe is not an reversible process. Whatever happening inside the universe cannot be reversed back. So that is also wrong, and none of this is also wrong. Okay, so based on entropy principle, an isolated system that is irreversible system, the entropy of that system also always increase and never decrease, and this entropy remains constant for isolated reversible system only. But universe as a whole is a irreversible system, irreversible isolated system, so entropy of this universe will always increase and will never decrease. Okay, so any doubt in this concept, any doubt in entropy principle, you can ask. Okay, any doubt? No? Okay, so now let's move to the, yeah, Shuru Malish. Okay, no doubt. Let's move to the next question. Okay, yeah. So the next question is, the performance of engineering systems is degraded by the presence of irreversibility. Yes. And the Planck space is a measure of magnitudes of irreversibility present during that process. Okay, before going to this question, Mothi Krishnan asked a question. Sir, then the whole system in the universe. Mothi, I didn't get you. Let me reiterate. Uh, you are asking that the whole system in universe. So what I got from your question is, you are asking if we are considering the whole system as universe or universe as a whole system. So uh, let me tell you, universe is a surrounding. Universe is a surrounding. Okay, so yeah, so system is always with respect to its surrounding. You got it? So if we consider a small volume, or for example, in your room, if you have a bottle, and if you consider that bottle as a system, then apart from that bottle, whatever is there inside the room is a surrounding to that bottle. But if you consider that whole room as a system, then the bottle is also a system, and any other things that are in your room are also a part of system. But apart from that is surrounding. Similarly, uh, when we consider the whole universe, so the whole universe can be considered as isolated system, because we don't know, or we don't have any uh, you know any proof that the whole universe interact with anything else. So the whole universe can be considered as an isolated system that doesn't interact with the outside. And for that isolated system, that is a universe, we can talk about this entropy, change in entropy, and all other concepts. Okay, so I hope you get the answer. Did you get it? Okay. And Nishant Kumar, yes, Nishant, ask.
No, sir.
Okay, okay,
All clear.
okay. Yeah. So to the next question, the performance of engineering systems is degraded by the presence of irreversibility, and the blank space is a measure of magnitudes of irreversibility present during that process. So here is an statement, and the second part is the question. So the first statement is, the performance of any engineering system is degraded by the presence of irreversibility. Okay, so it is saying for any engineering system there is an irreversibility, and it degrades the performance of this system. That is correct. And the second part is, what is the measure of magnitude of irreversibility present in that process. Okay, so again, go to the entropy principle. So again, that Clausius inequality tells us that ds is greater or equal to dq by t, and for irreversible process it is del as ds is greater than dq by t. Okay, so to convert this inequality into equality, so ds can be written as ds is equal to dq by t plus some s gen. That is a term that includes the irreversibility. Okay, so as you can see, that's entropy, the ds, the change in entropy of this irreversible system is dq by t plus s gen, and this s gen considers the irreversibility in this process. Okay, so this s gen, that is also called as entropy generation. So the value of this entropy generation, the S gen, tells us the amount of irreversibility and in any irreversible system. Okay. So again, go to the question. What is the measure of magnitude of irreversibility present during that process? So this entropy generation is the measure of magnitude of irreversibility. Higher the irreversibility, higher the value of S generation. Okay. So going to the options, Exergy is a measure of magnitude of irreversibility. No, this is wrong. Entropy generation is a measure of magnitude of irreversibility. Yes, this is the correct answer. And the entropy is a measure of irreversibility. No, entropy entropy is fixed at an state or at a point, so it is not the measure of irreversibility. But yes, entropy generation is the measure of irreversibility, and this fourth option is not valid as well. So the entropy generation, the term entropy generation is the measure of magnitude of irreversibility. Okay, that is the answer, and that we derived from the Clausius inequality again. Okay, so any doubt in this question?
Yes, sir. Sir,
Yeah,
entropy generation, how can measure? How can measure entropy generation?
how can measure?
Yes, sir. Entropy generation.
Okay, so in an irreversible system that goes from point one, see, like this system is there, it goes from this point one to point two. Okay, so point one,
Yes, sir.
so point one and point two are states of the system, and you can measure these states of the system. Okay, temperature, volume, pressure, and all those things. And from those state values, you can calculate the value of this entropy. Okay, and once you get the values of entropy, and you know in this process from 1 to 2 how much heat you have transferred, that is dq. Okay, so you now know the second term as well, dq by t. Okay, and you measure d as the entropy, and the difference of this ds and dq by t is the entropy generation. Okay, so in this way the entropy generation can be measured. Okay,
Okay, sir.
because for reversible system dq by t is given, dq by t is there, ds can be measured by the end states, so as generation can be calculated from those two values. Okay, okay, and how can I get notes? So I will upload these ppts on drive, and you will get the link for that drive as well. Okay, so yeah, I will make it sure that you get those ppts as well. Okay, Biman. Yeah, so entropy of universe is equal to entropy generation. Yes, yes, in last concept we saw that the entropy of universe is increasing, and that increase in entropy is the entropy generation. Okay, so any doubt till here? So let's move to the next question or next concept. Okay, so again, so Clausius statement of the second law. So what it says? So Clausius statement says it is impossible to construct a device which, operating in a cycle, will produce no effect other than the transfer of heat from a cooler body to a hotter body. Okay, so from here in the figure you can see the heat is being transferred from hot body to cold body. That is possible, and that is an spontaneous process. Okay, heat always flow from higher temperature body to low temperature body spontaneously. Okay, so this is possible, but the flow of heat from a cold body to hot body spontaneously is not possible. That is what Clausius statement of second law says. Okay, so it is impossible to construct a device which, operating in a cycle, will produce no effect other than the transfer of heat from a cooler body to a hotter body. Means heat transfer from cooler body to hotter body without any input. Okay, is not possible. So spontaneous flow of heat from cold body to hot body is not possible. So it is the statement of Clausius of second law. Now, what is the extension of this statement? The extension of this statement is to flow the heat from the lower temperature body to a higher temperature body. Some work must be expanded. Okay, some work should be done on the system so that it can flow the heat from lower temperature to higher temperature body. Okay, So this is the extension of Clausius statement of second law. Now let's see the next question. So the question is, in a refrigerator, heat is transferred from a lower temperature medium, that is the refrigerated space, to a higher temperature one, that is the kitchen air or outside air, and this is a violation of second law of thermodynamics. Okay, so here is a statement: a refrigerator transfers the heat from the lower temperature space, that is refrigerated space, to the higher temperature one, that is the kitchen air or outside air. So is it a violation of second law of thermodynamics? This is the question. So now we saw here the Clausius statement. Okay, so Clausius statement tells, if you want to transfer heat from a lower temperature body to higher temperature body, you must expand some work. Okay, now let's go to the question again. So here is the refrigeration cycle. So here you can see in the evaporator, the heat is being transferred from the cooler space to the evaporator. Then the liquid refrigerant goes to the compressor, where the work is done on the refrigerant, and then this heat is transferred to the outside air. So this is outside air. So here you can see that heat QL is being taken from cooler space, cooler body, and then it is being thrown to outside, that is at a higher temperature, hotter body. Okay, but here you can also see that some work is being expended on the system. So this W work is being expended on the system. So if you see, uh, we can see that again, that heat QL and QH. So again we can see that heat QL or Q2 at temperature T2, that is the lower temperature, is being transferred to the higher temperature body at T1, but with some work W. So these two systems are similar, and we can say from that Clausius statement, the expansion of Clausius statement, that the heat can be transferred from a cooler space to higher temperature space with the with some expense of some work, and this is being followed here. So uh, the principle of refrigerator doesn't violate the second law of thermodynamics, so this statement is false. Okay, so in a refrigerator, the heat is transferred from lower temperature to higher temperature with some expense of some work, and that followed the second law of thermodynamics very well. Okay, so this statement is false, and this, yeah, the answer is false. Okay, so any doubt till here?
No, sir, I don't have any doubt.
Okay, okay. Anyone else? Any doubt till here? Whatever we discussed, 8 or 10 question. Any doubt? Okay. So, so yes, this is all we have to discuss today, and the next session will be on next Tuesday at 6 p.m. So, I hope you guys will uh, turn out that day also, and also I will request you all guys, please watch videos so that you have uh, some clarity, and also you have some doubts, and then ask in these these sessions, so that your questions get cleared and you have some good concepts as well. So I will request you guys, please, please, please watch those videos, and then we will discuss further in the next sessions. Okay, so yeah, this is all from my side today, and hope to see you guys soon in the next session. Okay.
Okay, sir. Thank you.